Essentials of Data Transmission, Module 3, Signal and Noise. Signal and noise. In communication systems, the received waveform is usually categorized into the desired part containing the information and the extraneous or undesired part. The desired part is called signal, and the undesired part is called noise. Mathematical tools are used to describe signals and noise. Random signal. Information and noise are both random signals. Randomness or unpredictability, that is a key property of communication system. Random signals have statistical characteristics that may be measured. There are several important tools for characterizing random signals. Random processes. In a radio communication system, the received signal usually consists of an information bearing signal component, a random interference component, and channel noise. The information bearing signal may represent a voice signal that typically consists of randomly spaced bursts of energy of random duration. The interference components may represent spurious electromagnetic waves produced by other communication systems operating in the vicinity of the radio receiver. Noise. A major source of channel noise is thermal noise, which is caused by the random motion of the electrons in conductors and devices at the front end of the receiver. Thus, the received time-varying signal is random in nature. The combination of the concepts of time variation and random variables introduces the concept of random processes. Although it is not possible to predict the exact value of random signal or process in advance, it is possible to describe the signal in terms of statistical parameters. Gaussian processes. Gaussian random variables play a fundamental role in communication systems because many physical processes that generate noise in communication system can be considered approximately Gaussian distributed. The Gaussian random variable is mathematically trackable and therefore convenient to deal with. A Gaussian process plays an important role in the study of random processes due to Gaussian process has many properties that make analytic results possible. Random processes produced by physical phenomena are often such that a Gaussian model is appropriate. White noise. The noise analysis of communication systems is often based on an idealized noise process called white noise. The power spectral density of white noise is independent of frequency. White noise is analogous to the term white light in the sense that all frequency components are present in equal amounts. White noise. The white noise parameters are usually measured at the input stage of a communication receiver. Since there is no delta function at the origin in the power spectral density, white noise has no DC power or the average value is 0. As long as the bandwidth of a noise process at the input of a system is larger than that of the system itself, we may model the noise process as white noise. Noise in digital communication. Digital communication has been replacing existing analog communication with new communication services. The reason for evolution in communication methods is the greater noise tolerance provided and the almost exact reproducibility of digital sequences at the receiver. The strong external reasons for the increased dominance of digital communications are the rapid growth of machine-to-machine communications. Noise in digital communications. In addition, the ability to further improve the robustness of digital communications through the use of error correction code is an important advantage over analog. As digital communication have greater noise tolerance than analog, digital communications are applied in demanding situations. Noise can still have significant effect on digital communications. Bit error rate. In digital systems, the output quality of the information is of primary concern. Since the information is digital, the quality is measured in terms of the average bit error rate or BER. A bit error occurs whenever the transmitted bit and the corresponding received bit do not agree. Bit error rate. If n denote the number of bit errors observed in a sequence of bits of length n, then the relative frequency definition of BER is as displayed. Bit error rate BER is the figure of merit for comparing digital communication systems. BER is typically not a linear function of the signal to noise ratio.